Okay, so to set up the first law of thermodynamics, let's actually step back for a second to think about how we keep track of energy for mechanical systems. Because fundamentally what the first law of thermodynamics is about is it's about keeping track of energy. So when we talk about mechanical systems, basically this is certainly the most common way that we've chosen to keep track of mechanical energy. We said we can keep track of the kinetic and potential energy at some initial point. You can keep track of the kinetic and final energy at some final point, and then you can keep track of the work done by non-conservative forces as it goes from the initial state to the final state. And so if we rearrange these terms, right, so we basically just take these two initial terms and bring them over the other side, then I notice what I get is K final minus K initial, or that's just the change in kinetic energy, plus U final minus U initial, that's just the change in potential energy. That's just another way of saying the change in the mechanical energy of my system. And so this gives me that the change in the mechanical energy of my system is equal to the work done by non-conservative forces. And what we said before was when the work done by non-conservative forces is zero, then the total mechanical energy of your system doesn't change, which means the mechanical energy is conserved. But another way to think about this equation is that keeping track of how the energy changes in a mechanical system is all about keeping track of the work done on a system by non-conservative forces. So if you want to keep track of how the energy does change, you want to think about how the total energy of your mechanical system, its energy changes. You want to think about how non-conservative forces are doing work. Do you have non-conservative forces doing work to add energy? Do you have non-conservative forces doing work to take away energy? And then again, when the work done by non-conservative forces is zero, then the energy of a mechanical system doesn't change. Doesn't change is just another way of saying that the energy is constant, which is just another way of saying that the energy is conserved. Right? So with this framework in mind, let's talk about the first law of thermodynamics. So the first law of thermodynamics tells us that the change in the total energy of your system is equal to the energy transferred as heat minus the work done by the system. So this is how we're going to keep track of energy for thermodynamic systems, just like our K initial plus U initial plus work done by non-conservative forces equals K final plus U final equation was how we kept track of energy in mechanical systems. So part of what this tells us is that keeping track of how the energy changes in a thermodynamic system is all about keeping track of the energy transferred into or out of the system as heat and the energy transferred into or out of the system through work. So in some sense, all we're doing is saying there's an additional term, this heat term, this energy transferred as heat, when we deal with thermodynamic systems. So let's talk about that term first. One, again, it's Q. It's the energy transferred into or out of the system as heat. And Q will be positive, right? Q has a positive value if energy is transferred into the system. So you're increasing the energy by transferring in a positive amount of energy as heat. If Q is negative, then energy is transferred out of the system. And so Q is fairly straightforward in terms of its interpretation. The work term is a little more subtle. So notice one of the things is we've got a subscript here that says the work by. There are two ways you can talk about the work. And in fact, the way that I typically choose to talk about the work is opposite of the way that your book talks about the work. So I'm going to talk about the work done by the system. So I'm going to make the choice of saying I'm going to keep track of how the system does work, and when the system does positive work, it's got to get rid of that energy, which is why there's a minus sign there. The book chooses to keep track of the work done on the system. So your book's equation is actually the change in energy is equal to Q plus the work on. And so it just says you can add energy to a system as heat, or you can add energy to a system by doing work on it. Effectively, they're telling you the same thing because those two works relate very simply. So the work done by the system is equal to negative the work done on it. So if the work If the system does positive work, then the work done on the system by external forces was negative. If the work by external forces was positive, then the work done by the system was negative. And so you can always relate these two things to each other, so it just really becomes a convention in terms of how you choose to set up the first law of thermodynamics in terms of the work term. So again, from the way that we're going to deal with it, let's imagine that we've got a piston. And so all I've got here is I've got some gas inside a cylinder, there's a piston on that cylinder, and then that piston can move back and forth in response to what's going on with the gas or what's going on with external forces out here. And so let's say that what you had was a force exerted by the gas that pushed the piston from its position here out to some further away position. Okay? In that case, the work done by the system would be positive. The force exerted by the system, the displacement of the piston, both those two things are in the same direction, so the work done by the system would be positive. If, on the other hand, let's say that the gas is pushing against the cylinder, but there's something else out here that pushes even harder, and so the cylinder head, the piston head here moves in. In that case, the work done by the gas would be negative, because it's trying to push that piston head out, and instead it moved in. So our rules still apply in terms of thinking about the force exerted by the system, and the displacement of this piston is going to tell us, the relative direction of those two forces is going to tell us what the sign is for that work term. And so what it means is that the work done by the system will be positive when the volume increases. So if the force exerted here by the gas pushes the piston out, then the volume of the gas is going to increase, which means that the system expands, and the work done by the gas will be positive, the work done on the gas will be negative. If, on the other hand, the volume decreases, so the piston head is pushed in, then the work done by the gas is actually negative, force displacement point in opposite directions. The work done on the gas would be positive, so it took some larger external force out here to get the system to compress. And so we're going to end up focusing on, is the system expanding or compressing? And that's going to tell us something about whether the work being done by the system is positive or negative. So from our definition of work, we know that we can calculate the work done by the system to be an integral from some initial to some final position of the force exerted by the system times our little differential displacement here. And all we're going to do, and then graphically, this equation tells us that the work done by the system is just the area under the curve of a force versus position plot. Well, all we're going to do is basically take exactly that equation and just multiply in by this particular version of the number 1. So again, this is just a over a, so this is really just the number 1, so I can get away with multiplying anything by the number 1 and not changing it. But here I've picked this particular special version so that the number 1 is written as the area the force is exerted over divided by the area the force is exerted over, and then I can rearrange those terms. Now part of why I do that is because Fx over a, right, this force per area, is another way of saying the pressure. So this is the pressure exerted by the system. So the gas inside that cylinder exerts some pressure on the piston, and that's what this is able to measure. This second term here, area times some little differential element perpendicular to the area, gives me some tiny little differential volume. So V here is the volume of the system. So what this means is I can also write the work done by my system as being some integral from an initial volume to a final volume of pressure times a little differential volume element. And so this is why thinking about how the system expands or compresses is actually going to tell me about what's going on with the work, because clearly I care about how the volume changes. The other thing that this equation gives me is it gives me a way to calculate the work done by the system graphically. It says I can look at the area under the curve in a pressure versus volume plot, which is also known as a PV diagram. So we'll spend a lot of time looking at PV diagrams, and one of the things that we'll be able to do, hopefully very quickly, is figure out whether the work done by the system is positive or negative based on whether we're expanding or compressing in the PV diagram.